over here. All right. Oh my God, this is so cute. Okay, so a couple of things once you get down to that point. Number one, you got a current term. You got the size of the area within the loop. All right, so this is known as the area of the loop. And you got the magnetic field, which is going to be intercepted by that loop. And then you got this angle. So the question is the angle of what? And what is the meaning of this term that we're looking at? All right, the combinations of the current times the area that you're looking at has a special name. All right, current times the area times the number of turns that you have is known as the magnetic dipole moment. All right, so that's what we're going to be interested in. It's known as the magnetic dipole moment. So N is the number of turns that you got. I is going to represent the current within this loop. All right, so let's add that into this. So we can see that the current is going up in a given direction. So there's current involved in this one. And A represents the area of this loop. All right, so this expression involving the number of turns, the current inside the loop, and the area of the loop is known as the magnetic dipole moment. All right, so what's the meaning of it? Guys, this is a bit of a mathematical expression, which has an abstract meaning. The real meaning of it, from my perspective, is this tells you how much this loop is going to act like a magnet. All right, so this is an expression that tells me how much the loop is going to act like a magnet. All right, so magnetic dipole moment, which means that because of the fact that it's got a current, it's acting like a magnet. Another thing that I'm noticing is it's got a direction of this thing as a direction. So it's going to be magnetized in this direction, which means that it's going to act like a magnet in this direction. And it's going to act like an electromagnet in this direction. That's it. Its tendency to act like a magnet is what I refer to as the magnetic dipole moment. So the bigger the current is, stronger magnet it becomes. Stronger of a magnet than it becomes. The bigger the area is, the stronger of a magnet than it becomes. Its tendency to become or act like a magnet is the most commonsensical definition that I could come up with for something like that. All right, so let me just add a few more things here. So it's going to have a direction. All right, so which means that it's going to act like a vector. And the weird part of it is, because it's acting like a vector, and because it's acting like a magnet, it's going to have a tendency to line itself up in the direction of the external magnetic field. All right. So in order to do that, what it's going to do is it's going to, in order to actually line itself up in the direction of the external magnetic field, I'm placing an angle there. Oh my God, okay, just leave it like that. It's going to experience a torque in this direction. Got it? So all of a sudden, I can rewrite the expression for torque in terms of the tendency of this current loop, magnetized current loop, to line itself up in the direction of the external magnetic field. It's going to experience a torque. All right, that's it. So this becomes mu times b times the angle, sine of the angle in between. And that happens to be that expression. Okay. All right, so I end up using this. The same explanation is located right here. So the torque is going to come about when the magnetic dipole moment tries to align itself in the direction of the external magnetic field. That's it. Simple expression. So the magnetic dipole moment represents the tendency of a current circuit to act like a magnet. All right. I like to make up my own little explanations in order to make sense out of physics, or else things. The term magnetic dipole moment is like, ugh. It's a meaningless statement unless you can attach some meaning to it. So this kind of tells me something about the tendency of a loop to act like a magnet, which has direction. So that's also going to have a tendency to line itself up in the direction of the external magnetic field. All right, so this expression of torque from physics 1, okay, so it goes through its permutations, you do the derivations, and then you come up with an expression, and then you look at the expression. Obviously, this current times the area of the loop. This has to be some kind of a vector expression, and then you have B, that's the vector itself, and then you got the sign of the angle in between, you got the torque itself is a vector. Obviously, you can express everything that we talked about in terms of a cross product, but you have to attach meaning to this expression. And the meaning that you can attach to that expression is obviously current causes magnetism, right? All right, so the current causes some kind of magnetism within the area of the loop. And how much magnetism it's going to cause is going to depend on the number of turns. And all of a sudden, this loop acts like a magnet. And the tendency of it to act like a magnet is presented by this title, which is a magnetic dipole moment. There you go. All right. Okay, so let's go back. I was going to do a problem, but before we do a problem, I'm going to do a problem. I want to do the hydrogen atom problem using this because that's actually cute. Before we do that, let's just solidify this expression. Okay, so what is the magnetic dipole formula? So the magnetic moment formula, dipole formula is the same thing. So this is the formula that we got. Stronger the current is, the larger the magnetic moment is, more magnetized it's going to become. It's more magnetized it'll become. More like a magnet is going to act. All right. Proper unit. Well, you got your current, so it's going to be amps. You got your area, so it's going to be square meters. So that's a good one. So what happens to the magnetic dipole moment? Magnitude when the current is increases, so current goes up. Magnetic dipole moment goes up, so which means it starts to act like a stronger magnet. I think that's a good way of saying it. So what happens to the magnetic dipole moment magnitude when the radius increases? So if you increase the radius, obviously the area is going to increase, so it'll become more magnetized. It's going to act like a stronger magnet. So likewise, if you increase the area, the same thing is going to happen. All right, so magnetic dipole moment becomes stronger. What else? If you increase the number of turns inside the coil, once again, the magnetization factor is going to go up, so it's going to act more like a stronger magnet. All right, the better question is, I think this is an important question. So how is the direction of the magnetic dipole moment determined? Guys, use the right-hand rule. Use the right-hand rule. Line up your thumb in the direction of the area vector, and the fingers, okay, don't forget it. Line up, you can do it either way. Line up your thumb in the direction of the current. Your fingers around the wire is going to curl in the direction of the magnetic dipole moment. All right, that's one way of doing it. Okay, I kind of like this way as well. All right, most books usually prefer this. All right, so thumb, just get your thumb in the direction of the current. Your fingers will curl in the direction of the dipole moment, which is going to be coming out of the page. All right, so what is the formula for the magnetic torque acting in a current carrying wire loop? So we came up with this, so it's going to be a cross product. This tells you about the tendency of the magnetic dipole moment to line itself up in the direction of the external magnetic field. And it's going to happen because through experiencing a torque rotational force. The angle represents the angle between the magnetic dipole moment and the external magnetic field. I don't know why I deleted that. It shouldn't be deleted. This is important. All right, so what happens to the loop of wire if there's an angle between the magnetic dipole moment and the external field? It's going to experience a torque. All right, it's going to experience a torque in order to line itself up in the direction of the external magnetic field. All right, guys, take a break. We'll continue. Okay, let's get back to the PowerPoint briefly. Now let's set this up. All right, the electric motors. We got a nice little animation here. All right, so what's causing this motor to spin is the torque that it's experiencing. So instead of saying it's experiencing torque, there's a second way of saying it is it's trying to line up its magnetic dipole moment in the direction of the external magnetic field. So it's the same exact expression. So there are two ways of saying it. It's experiencing a torque, obviously, because of the magnetic field acting on the current carrying wire is going to cause a force on it, and it's going to end up rotating with respect to its pivot, so it's going to experience a torque with respect to it. And the second way of saying it, it's trying to line up its magnetic dipole moment in the direction of the external force. That's it. Okay. One of the things that I want you to notice, it's not that significant, but if you're an electrical engineering major, these are the little things that you have to kind of pay attention to. Notice that once the circuit lines itself up in the direction, once the dipole moment lines itself up in the direction of the external moment, okay, once the dipole moment lines itself up in the direction of the external magnetic field, that's when the rotation would normally stop. All right. So right at that point, notice that you got this red stripe. Okay, so when it kicks in, at that point, the current is going to stop right there. Notice that there's no current inside the wire, and there's no current here either at that point. Animation kind of got it wrong at that point. So, oh, I think they got it. All right. So there would be no currents at that point inside the wire. So there would be no torque, and what would cause it to spin is the rotational inertia at that point. Or else this thing would not keep spinning like that, because once it lines itself up, once the magnetic dipole moment lines itself up in the direction of the external magnetic field, at that point the spin motion would just stop. Okay, so it's the same concept. One more time, let's just go over it. Current is coming out of the page. Current is going into the page. All right, the magnetic field is from left to right, and it's going to experience a torque in this direction. The force is in the upward direction on this wire, and the force is in the downward direction on the other section of the wire. All right, notice that it says normal. Normal represents the direction of the magnetic dipole moment at that point. All right, so notice that what happens to the normal is going to line itself up in the direction of the direction of the external magnetic field. All right, that's what happens. Once it lines itself up in the direction of the external magnetic field, that's it, guys. It would stop spinning. That's what should happen. If there's current at that point, as soon as there's an alignment, it's downward. All right, let me ask you a question. What would happen if physically, if I were to go in there and then push this wire in this direction, in the opposite direction? So if I were to go in there and apply an external force on it, and this is my applied force, I'm going to push this in that direction using an applied force. All right, so you apply a force on it to push it, and you got the shaft here, so this is your point of rotation. This is your pivot. So what's going to happen if you push it in that direction? You're going to end up generating a torque in the opposite direction, right? And then what happens to the loop in that case? So you just push it this way, and then when you let it go, what happens? It's going to snap back. You push it this way, when you let it go, what happens? It's going to snap back. You push it, it's going to snap back. Do you guys notice that it's the same as lifting something up against gravity? Okay, so the amount of work that you do in order to displace this against the magnetic field is going to get stored within that loop as its potential energy. So what is that supposed to mean? That means that the magnetic field, let's say the magnetic force, is once again a conservative force. Got it? So the amount of work that you do against the magnetic field is going to become stored in that object. It's its potential energy. All right, so that's exactly what this one represents over here. All right, so notice that this magnetic dipole moment is going to want to line itself up in the direction of the magnetic field, so it's going to end up experiencing a torque in that direction. So physically, if I go there and then get this thing out of alignment, the amount of work that I do is going to go into the potential energy of the loop. So which means that the magnetic field is a conservative force field. That's what it means. So the electric field is a conservative force field. Magnetic field is a conservative force field. What else? Restoring force is a conservative force. All right, so now we are getting all these forces. So what is the angle represented in this formula? Once again, it's the angle between the magnetic dipole moment and the external magnetic field. And then question number 29 is the one that we just answered. The amount of work that you do in order to get the loop out of alignment with respect to the external magnetic field is going to become stored in that object, in that loop, as its potential energy. All right, so this brings us to the next point. I think there's probably a video here that will discuss. All right, so this is what I'm talking about. You end up getting this electric motor. Notice that there's a brush over here, and you have a half lane, whatever that is. All right, so the current is going up. It's going to go through the wires. It will come back down. And then when there's current, it's going to experience a rotational force, so it's going to experience a torque. And then notice that when the dipole moment lines itself up in the direction of the magnetic field, that's when you shut off the current. So the rotational inertia, the moment of inertia just carries it over, so it keeps spinning.